All right, so this unit, we're going to start scientific measurements. So we'll learn about, like, how do we know what unit we should measure in? How do we know how many digits to include in that unit? So to start off, how often do we use measurements? So besides my 3 ideas up here, when are some other times you use measurements? Okay, so maybe like making a recipe. How many of you bake or you cook? Okay, so we gotta make some measurements there. When else do you use measurements? Okay, woodworking. How many of you are like crafty and you can build things? Good. So you have to be able to measure. How many of you drove to school today? Okay, what kind of measurements do you make when you're driving?
Radius.
Okay, so maybe like the radius of your turn. What other measurements do you make? Distance. Okay, like when to turn. How many of you are looking down at your speedometer? Oh. That thing, yes. Okay, we're looking at that. We're measuring how fast you're going. You guys check that every now and then, right?
No.
Yes, good. How many of you measure your time? Like, do you have to measure your time in the morning so you know you're going to get to school on time? Good. Okay, so we use measurements all the time. In science, we'll also use measurements all the time. I want to start with what kind of units do we use? So when we measure in science, we use something called the SI system. SI stands for System International, or how we would probably say it is International System of Units, which is also called the metric system. Okay. So remember, all you need to write down in your notes is just those bold words. Okay, so units in science is metric. So next time you measure the width of the table over there, what unit are you going to measure in? Good. So we're going to use centimeters, no more inches. Yes? Yes. All right. So since we're going to measure in metric system, I just want to review kind of the basics of the metric system. So when we measure the length of an object, the base unit of the metric system is meter. And then the symbol for meter is just a lowercase m. Now let's say we want to measure something really tiny like the width of your pencil. Meter is probably too big, so what would you measure in instead of just a meter? Okay, maybe like a millimeter or maybe a centimeter, right? So just depending on what you're measuring, we could change this, right? Let's say we wanted to measure the distance from your house to the school. Meters might be too small of a unit, so what could you measure in? Good, like kilometers. When we measure mass, the base unit for mass is kilogram. Okay. Kilogram is just lowercase k, lowercase g. Why do you think mass is kilogram instead of just a gram? How small is a gram, you think? Teeny. Okay. Gram is a very small measurement, so the base unit is kilogram because most things weigh like a lot in grams. And how many of you like to work with huge numbers, like something to the 6th power? No one, right? So in metric, kilogram is the base unit just because gram is so tiny. Time, the standard unit is seconds. In seconds, it's just a lowercase s. Volume is measured in liters. Liters is a capital L. And then density can have 2 different units depending on which one like makes more sense. So density can be grams per cubic centimeter. You would use this unit, like if we did density today and you used your calculation form of the volume, right, if you actually used the 4/3 pi r cubed, your unit would have came out in centimeters cubed. Okay, so if your volume's in centimeters cubed, this is going to be your unit for density. Or another equally fine unit is just grams per milliliter. And that would be like if you did volume with the water displacement like you did today, that measurement comes out in milliliters. So then your unit for density is grams per milliliter. Okay. So either or of these are fine for density. It's just whichever one your volume's in is the one you use. And then finally, temperature can be in kelvins or Celsius. So the symbol for Kelvin is just a capital K, and then Celsius, it's that degrees, capital C. All right, so next we're going to look at some prefixes. We're not going to write all of these. I'll just star the ones that I want you to know. So the nice thing about the metric system, everything is a base 10. And so we can change our prefixes to fit our measurements better. So for example, earlier we talked about the base unit is meters, but let's say we wanted to measure like from here to Denver. That would be a lot of meters, right? So could we change our prefix to kilo and do kilometers? Okay. There are a few of these I want you to know. So one of them is kilometer. So the symbol for kilometer is just lowercase k, lowercase m. And then I also want you to know the relationship. So you need to know that for every 1 kilometer, there's 1,000 meters. The next one I want you to know is centimeters. Centimeter is just lowercase c, lowercase m. What does the prefix centi mean? 100, okay? So if you can remember that, then the relationship is easy to remember. There's 100 centimeters in a meter. And then I also want you to know millimeters. Okay, so millimeters symbol is little m. And then does anyone know what milli means? Okay, milli means 1,000. So there's 1,000 millimeters in a meter. Okay, so those 3 that are starred, you just need to know those 3. You need to memorize those 3. Sometimes we'll use other prefixes, like you might see micrometer or nanometer, but those you don't have to memorize. If we ever have like a problem with micrometer or nanometer, I'll either like give you this relationship or you can just Google it. Okay. But you need to know these 3 because they're super popular. You need to know kilo, centi, and milli. And then one other thing I want to point out is this example I gave you meter. But the nice thing about the metric unit, let's say we want to do liters. Okay. Is there such thing as a kiloliter? Yeah, so, and it's the same relationship, right? For every 1 kiloliter, there's still 1,000 liters. Is there such thing as a centiliter? Yeah, and it's the same relationship. 100 centiliters are in a liter. And are we familiar with milliliters? Good. Okay, so 1,000 milliliters still equal a meter. Could we do the same thing with grams? Yeah, so kind of the nice thing about the metric system, the prefixes and the relationships are the same for any of those base units. All right, so moving on, when we make measurements, we're going to make 2 different types of measurements in class. We'll make quantitative and qualitative. Down here, I like flip-flopped them from the title. So the first one we'll talk about is qualitative. And the word qualitative, think quality. Okay, so qualitative measurements are measuring qualities, or they're like descriptive, non-numeric forms. So for example, if someone's sick, a qualitative measurement you could make is you can feel their forehead. And if they have a fever, what are you going to feel? Hot. Like they're going to feel abnormally hot. Okay, so going off of feel, and you just say like, oh, they are abnormally hot, that's an example of a qualitative measurement. The other type is quantitative, and in quantitative, think quantity, okay, or think numbers. So quantitative measurements have numbers. So if we go back to the same type of example of someone feeling sick, this time your quantitative measurement is to give them a thermometer, and you're going to actually take their temperature with a thermometer, and you're going to get an actual number. So does that make sense, the difference? So qualitative, like descriptive, you're using words like their forehead feels hot. Quantitative is a number, their temperature is 101.3. Do we feel okay with the difference between those 2? Good. All right, so we're going to practice. I have just some statements up here. Some are quantitative, some are qualitative. I'm going to read them, and I just want you to tell me out loud if it's a qualitative measurement or a quantitative. Is it okay if you get it wrong? Yeah, so don't be afraid to try. The basketball is brown. Good. Qualitative. The diameter of the basketball is 31 centimeters. Okay, quantitative. has the number. The air pressure of the basketball is 12 pounds per square inch. Okay, quantitative. This gets cut off, but if you're looking on the Google slides, there's one more, and it says the surface of the basketball has indented seams. Okay, qualitative. Perfect. Next, we're going to talk about accuracy and precision. So in our everyday English language, these two words are used like synonyms. Like if you're being accurate and precise, they're almost like the same thing. But in science, when we're measuring, they have different meanings. So when we talk about being accurate with your measurements, we're talking about like how close a single measurement comes to the true value, or you could think of that as being correct. Okay, so like when you make a measurement in science, are you actually making the correct measurement? And then precision is how close several measurements are to the same value. So if you want to shorten that to one word, it's reproducible. Okay, so can you actually go measure the same thing 3 different times, and do you get the same number all 3 times? All right, who here plays basketball? You just play for fun. You like to play. You maybe watch it. We can relate to these pictures a little bit. All right, so this first one, what do you just notice about the picture over here? First one on the left. Okay.
Me playing.
Are they going to make it in the hoop?
No.
Okay. Are they also like all over the page?
Kind of.
Okay. Do we know anyone like this? Okay. Some of us will own up to it. Okay. So this is an example of what low accuracy and low precision looks like. Okay. Where are you aiming if you're playing basketball? Okay. You're aiming at the hoop, right? So this is low accuracy. Are the balls even close? Okay. It's also low precision because do you see how like they're not even close to each other? Yeah. This person, they're random, right? Not even close. Every try is you get something different. Okay, what do you notice about this picture?
They're like all on the same side.
They're off, but they're consistently off. How many of you know someone, it's like they always shoot to the left every single time? Okay, this is low accuracy because it's not in the hoop. However, it's high precision. Are they shooting at the same spot every single time?
Sure.
Good. And then finally, what do we notice about this one? They're good. Okay, high accuracy. They're getting it in the hoop every single time. High precision. Hold on. We have 1.5 more minutes. Let's finish this one because it's like our same thought. So here I have just words. They're either synonyms with accuracy or precision. I'm going to read them and you tell me, is it accurate or precise? Multiple measurements. Precise. Correct. Accuracy. Repeatable. Precise. Reproducible. Mine got cut off, but I think next is true value. Accuracy. Good. So then next, we just need to review scientific notation. So a lot of times in chem class, we're going to use really large numbers and really small numbers. So I just want to review scientific notation. Sometimes when I use this like recording software, my format gets messed up. So don't write this down. Write 2.5 times 10 to the third. Okay. And I want to start with just vocab. So the 2.5, this is what we call the coefficient. And then the 3 up here, this is what we call the exponent. So to start off, we just need to know the vocab words. So if I say coefficient or exponent, you know what number I'm referring to. All right, so I just want to practice converting numbers into scientific notation. Okay. So the first one we'll convert is 36,000. In 36,000 here, there's no decimal point, but if it's not shown, like where is it implied to be? Okay, so it's implied that it's at the end. And when we convert a number into scientific notation, you have to move the decimal in between the first 2 like non-zero digits. Okay, so the decimal needs to move so it's in between the 3 and the 6. So now all we have to do is count how many places does the decimal move. So it moves 1, 2, 3, 4. So when we write this into scientific notation, it just becomes 3.6 times 10 to the 4th power. Let me show you what it isn't because I get this all the time. Okay. Sometimes people like to just put it like after the 36. So incorrect scientific notation is 36 times 10 to the third power. Okay. It like rules for scientific notation state it has to be in between those first two non-zero digits. Okay. So we're going to write 3.6 times 10 to the fourth. No 36 times 10 to the third. Yes? You with me on that? Okay. You try the second one on your own. So convert 450 million into scientific notation. So you do this on your paper and then we'll check answers. Okay, let's check answers. Someone tell me, what did you get? Go ahead.
4.5x 10 to the 8th.
Good. So 4.5 times 10 to the 8th. Do you all agree?
Yeah.
Okay, good. No 45s times 10 to the 7s, yes? Okay, those are technically incorrect. It's 4.5 times 10 to the 8th. All right, let's look at the last one. This time we're going to convert 0.000598. Okay, this time the decimal point is given to you. Where am I going to move it to now? Okay, you're still going to move it in between the first two non-zero digits. So it's going to move in between the 5 and the 9. Okay. And then we're just going to count how many times do you have to move it. 2, 3, 4. So then we're going to write 5.98. And I moved it 4 decimals, but this time I moved it to the right, so it's to the negative fourth. Or another way you can think of it is this number is less than 1, correct? If your number is less than 1, then it's a negative exponent. Okay. And in chemistry class, we will use very, very large numbers, like to the 22nd or 23rd power. We will also use some really tiny numbers. So we need to get comfortable with like positive exponents and negative exponents. All right, so today we're mainly going to focus on how do we measure. So pause on like just copying down the slides. So for the remaining slides, I want you just to stick with me. So if you're on a previous or like you're moving forward, go ahead and pause and just make sure you're on my slide. A lot of these slides have like a ton of words. It's mainly for people if they were absent today, you could like read this whole paragraph, okay? You don't need hardly any slides or hardly any words for this slide. Even the bolded words down here, you still don't need to write all those. So let's go over this and then I'll show you like, you might need to write like 3 words down. Okay. So today our focus is when we measure, how many digits do I know, like am I gonna record in my measurement? Okay. So I'm gonna start with just this example. Let's say we're gonna measure your iPads, okay? Maybe we put it on like a really inexpensive postal scale. And the postal scale just gives you a weight of 2.4 grams. Okay. How many digits are in 2.4? 2. You're going to include, we call those significant figures, or sig figs for short. Okay, so this measurement has 2 sig figs. Then let's say we take your tablet and we put it on a little bit nicer scale. This time the scale can read 2.43 grams. Okay. How many digits are in 2.43? 3. So we would say this number has 3 significant figures or sig figs. And let's say we move your iPad and we put it on a really fancy scale called an analytical balance. And let's say it measures your tablet to be 2.4345 grams. How many digits is that? 5. Okay, so that balance has 5 significant figures. So when we use like digital reading instruments, they are already like calibrated to measure a certain number of significant figures. And so when you read something on digital, like our balances in this room are digital, you're going to include all the digits given, okay? Because the balances we own, they are already set up to include like the correct number of significant figures. Okay. So this one's super easy. When you read a digital readout, you just record all the digits displayed. So the only thing you need to write is just what I've underlined in blue. So whenever you have a digital readout, you're just copying all the numbers down. And these are nice because our digital like tools, they're doing all the work for you. If you have a tablet that can only read 2.4 grams, that's because that's all it knows. It doesn't have the capability to measure to the hundredths place. Okay, so you would only write 2.4. But if you have a really fancy instrument that could measure like 5 digits, you need to include all 5 because it means that that tool, it is capable of knowing that the tablet's 2.4345 grams. Okay, so however many numbers you get on a digital readout is what you include. Okay, you can't add any extra and you can't take it away. So let's say you're using our scales over like in this room. If our scales give you 2.4 grams, can you just add a couple zeros to the end and write like 2.40 or 2.400? No, because our scales, they couldn't measure to the hundreds or thousands place. Okay. Same thing, if you ever have a really fancy tool that can measure out to like the 10,000s place, you need to include that. Okay. All right, so digital instruments are super easy. Are you ready for the ones that are not as easy? Okay. The type of instruments that are not as easy to read are analog instruments. I'm going to have you copy what I want you to put in the notes first, then we'll do the example. But what I want you to have for an analog, that's like this. Do you see how you're given like 30 and then 31, and there's a little bit of interpretation you have to do? That's an analog readout. So what I want you to write down is analog readouts, you report 1 digit more than the smallest division. Okay. So I'm going to give you like a minute to copy that down, and then we'll do the example, because I want to make sure I have your attention when we do the example. All right, so take a look at this scale over here on the left. Okay, this is called a burette. Burettes are like long, skinny glass tubes, and liquid goes from top to bottom. So we're going to read this one from top to bottom. Okay. So the first thing we have to do is just figure out our scale. So this is 30. Down here is 31. So what does each individual little measurement line equal? Okay, 0.1, right? So this is 30.1, 30.2, 30.3, 30.4, 30.5, and so on. You with me there? Okay, that's step 1. So when I read this, I know it's past, so it's 30.1, 30.2. I know it's past 30.3. But it's not quite to 30.4, okay? So when we read analog, it's every digit you can see plus 1 more, okay? So we're sure it's past 30.3. So now you're gonna guess that very last digit. The way you guess is you're just gonna look in between the 0.3 and the 0.4, and I would recommend you kind of just break it up into tenths, okay? So if we were to like break this up into tenths, where do you think this line falls? Is it like 0.1, 0.2, 0.3, 0.4? Okay, like 1, 0.2. Okay, either of those are fine. Okay, I would read this as like 0.2. So it's like a 2/10 of the way there. So that last digit is my guess. So I would read this as 30.32. And if we're making measurements, what do you absolutely have to include? You need a unit. So if we're looking at volume, it'll be in milliliters. Okay. And we're going to practice this today. We're going to do lots of practice. Okay. But analog, it's every digit you see plus the last digit is your guess. Okay. All right, so since we made a guess in that reading, there's a little bit of uncertainty, right? Like if you're guessing, you're uncertain about it. Okay. So uncertainty is that last digit. Now, if you look at this slide, is this basically what we just wrote down? Okay. You do not need to rewrite this, right? Because in a measurement, all the digits are known precisely, plus the last digit is estimated. That is even true for our digital readouts, okay? It's just when you have a digital readout, the machine is guessing that last digit, okay? When it's analog, you're the one who has to guess it. So let me show you how uncertainty works, though. Let's say you're reading a thermometer, and it lies in between 24 degrees Celsius and 25 degrees Celsius, okay? You can see that. There's like lines on the thermometer. Then you have to make a little bit of a judgment call of, well, where does like the little line on the thermometer fall, okay? Where does it fall between 24 and 25? So let's say it looks like it falls about 24.3, okay? The first 2 digits are known. I'm positive it's 24. This digit is a guess. And so this digit becomes our uncertainty. So our true value is 24.3 degrees Celsius, plus or minus, in this case, it'll be a tenth because your guess is in the tenths place. Okay. So what that means is the true value is somewhere between 24.2 because I subtracted a tenth and 24.4 because I added a tenth. Okay. Will we ever know the true value of the liquid? We just know that it's somewhere between 24.2 and 24.4. Okay. And that's what this number means. All right, so I just want to show you a couple more examples of uncertainty. Okay, so how uncertainty works. For this one, let's just do these examples together. Okay. So to figure out the uncertainty in a measurement, you just look at the very last digit. So here's 24.2. Okay, this digit is in the tenths place, yes? Okay, so that means your uncertainty is plus or minus a tenth. So your range is somewhere 24.1 to 24.3. If we look at 32, your last digit is in the ones place. So then your uncertainty is plus or minus 1. What's 32 minus 1? Okay, what's 32 plus 1? Okay, so if your range is, if you guess 32, then your range is, it's really somewhere between 31 and 33. And then finally, let's say we measure 100.55. That last 5 is in the hundredths place. So then your uncertainty is just plus or minus 1/100th. Okay, so that means the true value of this measurement is 100.54 to 100.56. So if you look at my 3 examples, I gave you like different numbers to like different levels. So notice this first one I measured to the tenths place. Okay, my range is relatively small, right? 24.1 to 24.3 is a pretty small range. This one is only to the ones place. Is 31 to 33 a pretty big range? And then this, if you have a tool that can measure to the hundredths place, this is a tiny range, right? Like 100.54 to 100.56, like that's small. Like that's very little room for uncertainty. So the more digits you can measure, the better, right? It means the more certain you are about your measurement. All right, so now we're gonna practice measuring uncertainty. Okay, we're gonna do this together. So if you are not on this slide, get to this slide so we can practice. Okay, I want you all with me here. So these are a couple of graduated cylinders. I'm gonna zoom in. Okay. So the first thing we have to do is just figure out our scale. So this is 50 and this is 60. So what does each individual line represent?
21.
Okay, just check, make sure it fits. So if it's 1, 51, 52, 53, 54, 55, 56, 57, and so on. Do we feel confident it's 1? Okay, and then when we read a cylinder, do we read where it falls on the side or the bottom of the curve? Bottom. Anyone remember what we call this? The meniscus. Good. So you're going to read the very, very bottom. So if you're measuring in real life, what do you have to do to be able to see the meniscus? You're going to have to like squat down and get eye level with it. Okay. All right. Where does it look like the meniscus hits? What line is this? Okay. So we can feel pretty confident it's hitting 56, yes? Okay, but then when we read, we guess the last digit. Does it look like it is exactly on 56? Okay. To me, I think it does. So if I think it's exactly, I'm going to write 56.0. And you have to have a unit. What should your unit be for volume? Okay, milliliters. How many of you read this to be just a little bit above or below?
It looks slightly above.
Okay.
See the line, so maybe 0.1.
Okay, if you maybe read it slightly above, you would write 56.1 milliliters. Is that also okay? It is. Let me show you why. As long as our numbers, like our range, overlap, then you're okay. If we write 56.0, you're implying some uncertainty, which means you think it's 55.9 to 56.1 milliliters. Okay, so that's what that's actually telling you. If you write 56.1, you think it's 56.0 to 56.2 milliliters. Okay. Do these two ranges overlap? Yes. Okay. So like if you're wondering, like when you give an answer when you read, like how do you know if you would get it correct or incorrect? As long as like your uncertainty range overlaps with like the answer keys range, it would be considered correct. Okay. So like if I read 56.0 and my neighbor did 56.1, are we both okay? Yes. So no one panic. If you're off by like one digit, it's okay. Okay. Are we ready for the middle one? Okay. This is 3, this is 4. So what does each little line represent? Okay. 0.1. So this is 4.1, 4.2, 4.3, 4.4. You with me so far? Okay. So are we confident it's for sure 4.3? And then you have to guess that last digit. So now you have to make a little bit of a judgment of where does this line fall in between 0.3 and 0.4. So what do you think our next number should be? Okay, like another 3, like 4.33. Okay. Is it okay if you did 4.32? Is it okay if you did 4.44? 4.34. Good. Okay. Try this one on your own, and then we'll check answers. So I want you all to try it. Is it okay if you're wrong? Yes, it's okay. All right, so 20, 21, 22, 23, and then you have to make a judgment. Are you all close to 23.6? You did maybe 23.5, 23.4 even? Okay. Are you okay if I change the slide? Okay. Here's a few more. Let's have you try A and B. C is a little bit tricky, so I want you to try A and B on your own, and then we'll do C together. Okay, is anyone willing to share what they think A is? What do you have?
I got 16.9.
Okay,
Wait, did I read that?
16.9. Do y'all like give me like a thumbs up if you agree, thumbs down. No in the middles. Okay, is it okay if you did 16.8? Perfectly fine. Good. Okay, someone tell me, what do you think you have for B?
76.
Okay, 76. Why do you need the 0.0? Okay, yeah, right. You know it's for sure 76. You always have to guess that very last digit. Okay, so take it one digit further than you can read it. Okay, are you ready? C is what I call the tricky one. Are you ready for the tricky one? Okay. This is 4, this is 5. So what does each individual line have to be? 0.2. Okay. So this is 5.2. This is 5.4. Okay. So where do you think this line falls? Okay. This one has to just be 5.3 because are you already kind of guessing it's 5.3? There's no line in the middle that tells you it's for sure 3. Could it really be 5.2 something? Probably. Could it be 5.3 something? The 3 itself is a guess, so you can't go any digits further. Okay. That one I call is like the tricky one though, but are we okay with that? Okay. This time we're just going to look at some thermometers. So same idea, just different looking scales. All right, so we'll do this first one together. So here's 0, here's 10. What does each little measurement line equal? Okay, so then where do you read that to be? Okay, 8. And does it look like it's exactly 8? A little above, right on the line? What does this mean? Okay, so you're going to guess. If you think it's a little above, can you guess a different number? Sure. So one guess. This is a thermometer, so what should your unit be?
Celsius.
Okay, degrees Celsius. If you did like 8.1 degrees Celsius, is that fine? Sure. Okay, next we're in the negatives. So 0, 5, 10. So what does each little line have to be? Okay, because you're negatives, you got to go top down. So this would be negative 11, and this would be negative 12. Okay. So where do you think that falls? This one's kind of tricky. Go top down. So this is 11, this is 12. Is it somewhere in between 11 and 12? Okay, so it's going to be negative 11, and then you have to guess that last digit. Does it look about halfway there, 4/10 of the way there, 6/10 of the way there? Like 6/10? Okay, like 11.6. If you did 11.5, is that okay? Sure. Okay, you try the last one on your own. Oh, no, let's do this one together. All right, here we have 98, here we have 99. What does each little line mean? Okay, 2. So it's for sure past 98.6, but is it quite 98.8? Okay, it's in the middle. So what number are we going to write down? This one has to be 98.7. It's like that last cylinder we just did. We know it's for sure past 98.6, and we know it's not to 98.8. However, is guessing the 7 already our guess? Okay, you can't guess another number because this is the guess. Okay, do we